So what are we talking about? We are talking about fall in blood pressure. An example, fall in blood pressure. Okay, it is sensed by the mechanoreceptors which are located in the afferent arteriole as it enters the Bowman's capsule. Okay, and since there is fall in blood pressure, okay, the change in the change is pursued by the mechanotransduction. Okay, and that information is passed on to a type of cells which we called as what? Juxtaglomerular cells near the glomerulus, juxtaglomerular cells, and the juxtaglomerular cells in turn respond how? By releasing a substance, as if it is something great. What is the name of the substance? Renin. So if I call kidney as an endocrine gland, okay, then fill in the blank. The hormone it secretes may also be called as renin. As what? Renin. Okay, so renin may also be, not that everybody does, but it's okay. Can be considered as what? Endocrine, a hormone. Okay, good. And that renin acts on a substrate, and that substrate is called as what? Angiotensinogen, which is a very large protein molecule which is there in the blood, secreted by what organ? Liver. Secreted by what? Liver. What is the action of when the renin acts on the substrate angiotensinogen? It cleaves a tiny fragment, a small peptide which is about 10 amino acids long, and that tiny fragment is called as what? Angiotensin 1. Okay, and then as it flows along with the blood and passes through the lungs, it is acted upon by an enzyme which is called as what? Tell the full form.
Angiotensin converting enzyme.
Abbreviated as? Good. And under the influence of that enzyme, angiotensin 1 is converted into?
Angiotensin 2.
How many amino acids? 8 amino acids. And why are we so much worried about angiotensin 2?
Vasoconstriction.
So it's a very one of the most powerful vasoconstrictors encountered in biology. Therefore, we need to focus on this molecule, and we'll visit this molecule again and again. So here are the two structures. You can see angiotensin 1, angiotensin 2, and there you can see the capillary bed work at the arterioles. You can see the smooth muscles there. And on the smooth muscles, will they have a receptor for angiotensin 2? Yeah, they will. Okay, and when they are activated, those smooth muscles will undertake constriction and thereby increase the blood pressure. Just an example. Arterial pressure in mm. Okay, what have we done? Well, you have withdrawn. Okay, not a great experiment. Well, there is an accident. Okay, and there is hemorrhage. Okay, there is hemorrhage, and as a result of loss of blood, okay, there is a fall in blood pressure, and from 100, which is mean 100, approximately we are taking mean of what? Whatever is 80, 120, whatever. Okay, we have calculated it's about 100. And as a result of loss of huge volume of blood, the blood pressure has fallen where in this particular case? The mean blood pressure is 15, which is not a great idea. It's a bad idea. From the point of view of what organ it's a bad idea? It's a bad idea. Okay. And then if you as a result of that, as a result of what? As a result of fall of blood pressure, it will set off a chain of reactions which will begin at the level of juxtaglomerular. Hello? And then renin, and then angiotensin, and then angiotensin 1, and then angiotensin 2, and then it goes everywhere and acts on the smooth muscles. Okay, and the entire blood vascular system shows a profound constriction, and as a result of that, the blood pressure may be taken from 50 to 80 or something, the mean. Okay, so this one slide tells us the profound impact of angiotensin 2, and it also tells us how the organ kidney, okay, which is very interested in making sure that I get the blood supply at a proper pressure, and when I note that I am not getting enough proper pressure, I take the necessary means or the necessary steps. What is the step? Release renin. Do you get it? So what is the entire mechanism targeted as? Kidney wants to make sure that I must always get blood pressure which is 80, 90, whatever, ideally 100, okay, but for loss of, okay, so you got the message. So yeah.
Do all blood vessels have receptors for angiotensin?
No. They all of them don't have, but majority of the venous system, smooth muscles there they have. It's not uniform distribution, it is uneven, but for that you will have to go into details and but it's not even. I can talk about it later, but not at this stage. But your question is absolutely bona fide. It's different. Okay. We were just reading about ACE for a very long time. Okay, then ACE suddenly became very popular and very important. Okay, since COVID came. Okay, because it was realized that where is ACE sitting? ACE is sitting in the lungs. Okay, in the blood vessels of the lungs. Okay, it was realized that COVID virus, okay, enters our body through the ACE enzyme. Okay. So, although we have been calling ACE as ACE, okay, enzyme for a very long time, since 1920 people have started calling it as a receptor for COVID virus. Molecule is the same. What is the molecule? ACE. We consider it as what? Enzyme. Is it of course, it is an enzyme. Okay. But we have also started looking at the same molecule as what? Receptor. Receptor for what? COVID. Yeah. So, just read this interesting paper which came into prominence. Okay. And then of course, we discussed about this also. We need to briefly, Captopril, okay, it's a drug. Where is it? It's available in the market and people take it for the treatment of what? Hypertension and related conditions. Okay. And so, this is our fourth strategy for addressing the issues with reference to, and this is just one of the, so this is what? ACE inhibitor. What is this? This is ACE inhibitor. Okay. A typical treatment plan for hypertension will often include what and what and what? And good. So, what am I doing? I am slowly going from, if you see what we did yesterday and what we are doing today is, we first look at those molecules which are released by the cell and which act in the vicinity, in the neighborhood. Okay, and then we started talking of the molecules which act a little remote, comes from renin, acts on angiotensinogen which is somewhere. And now we are talking of yet another very interesting hormone, a hormone which has a profound influence on vasoconstriction. And this particular hormone comes from the hypothalamus. So, what am I looking at? There is okay, this is the human pituitary gland. What is it? Human pituitary gland. So, from this point onwards, from this point onwards, if you go couple of inches inside, you are going to get that organ which we call as pituitary. I am sure you have heard of. About half a gram in weight, very tiny, very interesting range of hormones. Okay. Now, this pituitary gland has two parts, anterior part and posterior part. I am not here to talk about the endocrine importance of the pituitary gland, about which I will talk in due course of time. Right now, our purpose is to focus on just one hormone, and that hormone I am sure you have heard of is called as vasopressin. Say that again. Say that again. Vasopressin. Okay, it's a nanopeptide. It's a peptide hormone made up of 9 amino acids, and interestingly, it is secreted by the posterior pituitary gland, but not synthesized there. Not synthesized. Where is it synthesized? It is synthesized in certain neurons, and those neurons, so here I have the pituitary gland and this is the part of the brain, and that part of the brain is called as hypothalamus. What do I call it as? Because it's the lower part of the thalamus, so hypothalamus, located below thalamus, hypothalamus. And in hypothalamus, author has shown 2 neurons. In reality, there are hundreds of neurons, and those neurons have the necessary machinery, mRNA and endoplasmic reticulum and Golgi complex, and they synthesize this peptide hormone, which is a large molecule, then cleaved, and finally you have arginine and vasopressin, which is a peptide hormone consisting of 9 amino acids. That molecule is trafficked along with the axons. Can you trace the axon from the hypothalamus into the posterior pituitary gland, please? Can you trace that axon? Great. And so the vasopressin hormone travels along with the axon. Okay, axonal transports mediated by a cytoskeletal system, and then it comes into the posterior pituitary gland, and in the posterior pituitary gland, it directly communicates with the capillary. Can you see the capillary there? And And if that neuron in the hypothalamus is excited and that neuron starts firing action potential, then the action potential will go from the pericardia or from the cell body all the way along the axon, and finally when the action potential arrives here, then it will release by exocytosis vasopressin. And where will the vasopressin go from there? It will go there, from there it will get into what? Capillaries. Get into what? Capillaries. So here we have a product which is synthesized by a neuron which gets into the blood. Therefore, I am going to call that molecule as a neurohormone. What will I call it as? Neuro. Why neuro? Because it is coming from a neuron. Okay. Why hormone? Because it is going in the blood. Okay. And so we have the neurohormone that is now being poured into the, therefore I can also call the posterior pituitary as, let us see if you make sense of this, neurohemal organ. Hello, what did I say? Neurohemal refers to blood, neurohemal organ. Okay. So the hormone goes from the neuron into the blood, and from there, from the blood it will go everywhere. Okay. Now why would this happen? This would happen because vasopressin is released in our system under two circumstances. One, when there is sudden loss of blood, you will get a lot of pouring of vasopressin. And secondly, if you are dehydrated, okay, you are moving out of sun, you sweat and don't get water to drink. Okay, when that happens for some time, okay, two things happen. Your throat gets dry, okay, that initiates behavior, and the behavior is start looking for water. Okay, if you get water, you will ingest water. Okay, that will happen. As simultaneously, your physiological response is that those cells in the hypothalamus will start releasing arginine and vasopressin will be released into the blood, and it will get into the blood, it will act on the kidney, and it will trigger a very interesting function of reabsorption of as much of water as possible from the urine, so that the urine becomes more concentrated and you are conserving water in your blood. I will talk more about it when we talk about the excretory system. But I am going to talk of yet another very important function of the vasopressin molecule, also known as vasopressin. It is also known by another name. Can somebody help me out? ADH, anti-diuretic hormone is the same. So when it acts on the kidney, I will call it as anti-diuretic hormone, and when it acts on the, arginine vasopressin, you can ask why arginine? Okay, arginine because that, okay, look at the structure in vasopressin there. Can you see that there? Can somebody tell me how many amino acids are there? 9. It is a nanopeptide. Okay. Can you look at the 8th peptide? What is the 8th peptide? Arginine. Okay. But you will say there are so many peptides, so many amino acids. Why am I worried about arginine? Why do I call it as arginine vasopressin? Interesting question. The answer to that question is, in all mammals, it is arginine vasopressin. But in pig, that arginine is replaced by lysine. Therefore, in the pig, this particular molecule, you will call it as what? Lysine vasopressin. But in humans and other mammals, it is what called as what? Therefore, that word arginine has stuck there for good. So, therefore, we call it as arginine vasopressin. Okay. So, that arginine vasopressin, when it comes from the pituitary, it will act on the smooth muscles of what? Blood vessels. Of what? Of some of the major veins and also some of the major arteries. What will it do? Vasopressin. Vaso is blood vessel. Pressin is press them, increase the constrict them. And now to go into some a few details. This is a peptide hormone. What hormone? Peptide hormone. It also takes a signal to the target cell by way of G protein coupled system, which is made up of 7 transdomain protein. Are you with me? Okay. So what do? I just go to the smooth muscle of the blood vessel. Okay. Tunica media. Hello. Tunica media. I have forgotten already. Okay. Externa, media, interna. Okay. Interna is same as endothelium. Media. So I take a smooth muscle cell from there, look at the plasma membrane, and in the plasma membrane I am going to find many receptors, but I am also going to find a receptor for what? Arginine vasopressin, and that receptor I will call as what type? Look at there, tell me. What is written there? V1 receptor. Where will I find it? V1 receptor. Now, I go to the kidney, in the kidney I go to the nephron, in the nephron I go to the collecting tubule. If you remember, fine, otherwise I will go to the collecting tubule, I will take a cell from there, from the cell I will take a plasma membrane, and there also I will get a G protein coupled system where arginine and vasopressin can bind, but I find that this receptor is different from that receptor, and I am going to call this receptor as what? V2, V2, okay. So, the action of arginine and pressin on these two organs is via two different receptors, and therefore, we call them as V for vasopressin, V1 and V2 receptors, very interesting. This is just to impress on your mind the profound importance of vasopressin in influencing the blood pressure. So, let us see, there is loss of blood, hemorrhage refers to what? Loss of blood, okay. And we are trying to standardize hemorrhage per ml per kg, how many ml? So, 5, 10, 15, 20, there is more hemorrhage, okay. And as a result of that, the pressure, whatever it was in the beginning, I will call 0. That may be, if it is human, it will be about 100. I will not call 100 as 100, I am calling 100 as what? 0. And I find that as there is a loss of blood, it will result in the what? Loss of what? Pressure, loss of pressure. I can see the loss of pressure from 0 it has gone to almost minus 20, 40, 60, and then I can correlate it with what? Vasopressin release. Okay, so there is a clear correlation as pressure goes on falling, vasopressin goes on releasing, and therefore what will the vasopressin do? It will release the, okay, what will vasopressin do? As a result of the action of the vasopressin on the smooth muscle, the total volume available for your 5-liter blood, hello, you are healthy, okay, how much blood do you have? 5 liters. Where is it accommodated? It is accommodated in your closed cardiovascular system, okay. Now, as a result of hemorrhage, okay, you are losing blood, so the blood pressure will fall, okay. As a result of the effect of arginine vasopressin, because now the volume is reduced, the pressure will be maintained, okay. So, you are still doing good, okay, although you have lost blood, because our vascular system has got elastic vascular system, okay, you are good with 5 liters, I will accommodate 5 liters, but if you have dropped down from 5 liters to 4.5 liters, I will constrict the entire blood vascular system so that my blood pressure still remains okay. Yes.
Which effect is more dominant, the effect of vasopressin or angiotensin?
I don't know. You have to read. You read and tell me. Okay. I don't know. Good question, good answer. Both equally relevant. No, question relevant, answer irrelevant. Okay. Just see it's a total, now this is almost a locally acting substance, but it is very important. You know, if there is a wound, okay, if there is a wound, our physiological system must come to our rescue, and one of the immediate problems is loss of blood, okay. To stop that loss of blood stop the loss of blood, okay, what the hormone is released from the endothelium cells, therefore the name is called as endothelin, okay, and it constricts the tiny blood vessels, not the large ones, but the tiny ones. What is the aim? Just to make sure that if the blood vessels constrict, okay, you will prevent the loss, okay. So, this is yet another substance which is again a peptide, and which plays an interesting role in, okay. Now, we will go to the, we have already done this once, we will do it once again. Why? Because at the highest level, we are talking of different levels of control, okay. We have seen the local level, we have seen the endocrine level, the hormonal level, and we are seeing ultimately it is the nervous regulation of the circulation, which we have already seen, and we know that there is a what? Autonomous nervous system divided into sympathetic and parasympathetic. Sympathetic is also called as thoracolumbar. What is it? thoracolumbar. Why? Because the neurons are located in the located in the thorax and lumbar. The preganglionic neurons, they give rise to preganglionic fiber. Preganglionic fiber will talk to the postganglionic neuron. The postganglionic neuron will give rise to fiber, and it is the postganglionic neuron which will terminate where? It will terminate in 100 places. But right now, because I am talking about circulatory system, I am talking about what? I am talking about the end, the terminals of the postganglionic fiber on the heart. And on the red ones are what are those red and blue tubes there? Arteries and veins. Okay, and so we have the arteries and veins being supplied by what? By the sympathetic nervous system, and we have already seen what? We have already seen that via by acting via the alpha 1 receptors. Okay, in your visceral organs there will be constriction, and if you are running somewhere, okay, and then via the beta 2 receptors dilate there. So it is managing the traffic of blood from one organ where it is not as much required to the organ where it is required. Okay, now will the sympathetic postganglionic fibers supply the capillaries? Get the question? Do they supply the capillaries? The answer to that question is no. They do not supply the capillaries. They supply the earlier part of the capillaries and they supply the latter part of the capillaries, because capillaries per se do not have smooth muscles. Never forget that. Capillaries have no smooth muscles, no, and the target is smooth muscle. So, what is the point in going to the capillaries? So, to emphasize that point, in this of course, the blood is the oxygenated blood is coming, arteriole, meta-arteriole, and then it is entering into the capillary venule. So, in this part you will not have any innervation, nerve supply of the parasympathetic nervous system, but before and after, yes. Okay, and depending on the type of receptors, you will get the response of contraction or dilation or whatever is. I put this slide just to have a profound effect of what can norepinephrine do to your vascular system. Profound effect. Well, very simple. You take a dog, okay, and inject. But before injection, make sure that you are monitoring the blood pressure, okay, and you inject. And you find little change, not a great change. But you say it's such a powerful molecule, why am I not getting a great change? You are not getting a great change because the moment you give norepinephrine and you start seeing the effect, the compensatory mechanisms start operating, okay, and you do not see a great change. Okay, because the physiological systems are continuously monitoring your blood pressure and giving out necessary corrective signals. I want to stop the corrective signals. So, what I do is I will inject an anesthetic like substance in the spinal cord. Okay. So, are the compensatory, what have I done? What I have really done is I have now killed the compensatory processes. So, the moment I kill the so this is the mean blood pressure there is about 100. Are you with me there? And then the moment I give an anesthetic like substance in the spinal cord, what happens to the blood pressure? It falls. Okay. And then when it has fallen, then I give an injection of norepinephrine. So, what I see is an effect of norepinephrine which is not camouflaged by, which is not hidden by any compensatory mechanism. I see naked effect of norepinephrine, and it is profound. And it remains for another interesting thing. Just look at the x-axis and tell me how long do you think the effect of norepinephrine is lasting? 5 seconds. 5 seconds. How long? 5 seconds. Yeah. Because there are enough enzymes even in the blood to break down the molecule. Therefore, one point I want you to remember is that the biological half-life of norepinephrine is 5, 10, 15 seconds. 15 seconds. What is the biological half-life of insulin?
6 months.
Very good. Only one answer. How long? 6 minutes. And what is the biological half-life of norepinephrine?
5 and 15.
Yeah, 5 to 15 seconds, that is all.
Does the fall of arterial pressure occur because of the loss in or fall in the tonicity of the blood?
Which one?
Here.
This.
Yeah.
No, this is because it is broken down. It's broken down. It's the you give norepinephrine, you get the effect, but epinephrine is so rapidly broken down.
Not the norepinephrine. The after administering the.
You mean this? You mean this? Okay.
Does it fall off because of the loss in tonicity?
Oh no, you have it everything. The responses, the response. I mean, you see, you have given norepinephrine, okay, because you gave norepinephrine to an intact animal, okay. So it should stimulate the entire cardiovascular system and increase the blood pressure. But at the same time, then there are compensatory mechanisms. It means it may be because, okay, the information may go to the medulla oblongata. From the medulla oblongata, it will the information may come down via the vagus. It will go preganglionic, postganglionic, release acetylcholine, and it may have negative effect on the heart. Okay, there are 10 compensatory mechanisms. All of them put together, I don't get a strong effect. So, but because I want to see the effect of norepinephrine per se, therefore I silence the system and I get. So, the aim of is only to, but okay, I think I'll just move on. Okay. We have done this, I am doing it again. I'll do it 10 times if it's necessary. It is so fundamental. Some of the preganglionic fibers of the sympathetic nervous system, what did I say? Some preganglionic fibers, okay, they terminate on the, so where, what do I have here? I have here the spinal cord. Are you okay so far? Spinal cord. In the spinal cord, my cartoon shows a single neuron, okay, so far. I call this as a neuron 1 of the sympathetic nervous system. It gives rise to a fiber. That fiber comes out of the spinal cord. Are you okay so far? And it goes and terminates on the second neuron, because autonomous nervous system must have 2 neurons in a series. So, it must go to the second neuron. In this particular case, the second neuron happens to be nothing but adrenal medulla. Nothing but what? Adrenal medulla. So, the cells of the adrenal medulla are getting a nerve supply from what? From preganglionic fibers of the, you are right, you are absolutely correct, preganglionic fibers of the sympathetic nervous system. Are you okay so far? Now, fill in the blank, fill in the blank. The neurotransmitter, fill in the blank. What is the nature of this neuron? Very good. Say that loudly. Excellent. Say that again. Acetylcholinergic neuron you can call. Okay. And therefore, if this neuron is acetylcholinergic, then my cells of the medulla here on their plasma membrane, what kind of transmitter are you going to find? Cholinergic receptor. But the moment you use the word cholinergic receptor, my counter question is going to be what type? What subtype? Nicotinic. Very good. Say that again. Nicotinic. So, on the plasma membrane of the cells of your adrenal medulla, you are going to get what kind of receptor? Nicotinic. Nicotinic. Nicotinic means what? 5 subunits ionotropic. 5 subunits ionotropic. So, whenever acetylcholine will combine on it, it will open, it will allow the sodium ions to go through, and then these neurons will be stimulated. What neurons? The neurons of the medulla will be stimulated. Are you okay so far? These neurons of the medulla, they do not have post ganglionic fiber. They have these are the neurons which are endocrine. Okay, these are the neurons of what? They are endocrine neurons, and they pour their secretion. They pour their secretion in what? Blood. Where is it going? It's an endocrine gland. Come on, it's an endocrine gland. So, where will its secretion go? In the blood. In the blood. So, we are talking of what? Adrenal. Talking of adrenal medulla. Adrenal medulla, you see, it's interesting because it synthesizes 2 hormones. It's an endocrine gland, it synthesizes 2 hormones. One is very familiar, norepinephrine or noradrenaline. And the second molecule it also synthesizes adrenaline. Adrenaline. What is it? Adrenaline. So, if I ask you a question, tell me what are the sources for noradrenaline in your body, dash and dash, fill in the blanks. Fill in the blank. These are the 2 sources of our norepinephrine in your body, dash and dash. What are you going to write there? Adrenal medulla, and the other one? Postganglionic. Very good, very good. Postganglionic fibers of the sympathetic nervous system. There are 2 sources. Okay. But my next question is going to be, tell me what is the source for adrenaline? There is only one. There is only one. What is it? Adrenal medulla. Good. You know something? You get lot of noradrenaline in your brain also. In your brain, you get a lot of noradrenaline. There is a very elaborate system of neurons, okay, which is continuously secreting noradrenaline and which is allowing you to focus your brain on a particular topic that you are interested in. Okay, okay. If that system sleeps, you will also sleep. Noradrenaline is so special in your brain. That's a separate system. That's in the brain. Okay, so we have one independent system which uses noradrenaline as a molecule for communication in the brain. One. Second is noradrenaline as a molecule in the postganglionic fibers of the sympathetic nervous system, where noradrenaline is released on specific targets like heart and blood vessels. 2. And number 3, noradrenaline is released from the cells of the medulla, which is a hormone which goes in the blood and acts everywhere. Wherever you will get adrenergic receptors, alpha 1, 2, 3 type of receptors, there you will get the action of noradrenaline or nor-epinephrine. You can read about this in this slide. You can read about that. You can read about that. And okay, now we have done this once. We'll do it once again. You remember this? Why did we do this? It's a very familiar figure. Very familiar figure. We did it in context of what? Context of what? Homeostasis. Homeostasis. Excellent. Did it in relation to what? Homeostasis. Okay, let's focus more on this. So here you have the heart, here you have the aorta. From the aorta you get the branches of the carotids, and as the carotids go, somewhere in your neck they swell a little, and you call it as carotid sinus. What do you call it as? Carotid sinus. And the carotid sinus and your aorta, they are being innervated by the fibers, by the sensory fibers. We have done it, and we have also done that. They are mechanoreceptors, and they take information from aorta over the 10th cranial nerve, which is also known as vagus. Very good. And the information from the carotid body is taken over the 9th cranial nerve, which is known as glossopharyngeal, and the information is taken to the medulla oblongata, and that's how the medulla oblongata is continuously monitoring the stretch on these vessels, and the stretch can be translated, or and provide information about the pressure which is being exerted by the blood at every systole and diastole. Good. Now what I'll do is I'm going to put an electrode on the blood vessel that takes from where? Okay, baroreceptor response, membrane potential in millivolts. Baroreceptor. Where are baroreceptors? We saw in the previous slide. They are in two places, either in the carotid sinus or in the aorta. I am going to take one of them, and I am going to place my electrode and monitor the voltage differences that are there. Good. And then the second I am going to do is I am going to monitor the arterial pressure. Okay. And I find that as long as in this particular case the arterial pressure is between 110/70 systolic diastolic, 1 systolic diastolic. Look, what am I recording? My electrode is on the baroreceptor, is on the aorta and there. Okay, I am recording from there. I find that I get the action potentials from those baroreceptors, which are sensory nerve terminals, at a particular frequency, which frequency is denoted there. Having explained to that, can somebody tell me what is the correlation? What is the change from the first column to the second column? It's there. You tell me it's there. What is it? If for any reason the blood pressure goes that much, then what is happening to the frequency? Is increased, and opposite, you can see the frequency has gone down. Okay, so the blood pressure. This is how the blood pressure. Okay, the information about blood pressure is being communicated to your medulla oblongata. Are you getting?
Sir,
Yes.
here if the blood, can you go to that slide? If the blood pressure oscillates between something like 150 to low for like 40, we'll get the same as there being no effect.
It is more sensitive to the higher pressure. More sensitive. Your question is correct. It's sensitive to the higher pressure. But you know something? You are normal. You are in the first column. Okay. Then you develop blood pressure. Okay. So the moment you develop, you may go to second column. So you remain in the second column for a few hours, and then you come back to the first column, because the receptors are habituated. So they are sensitive to the change. Okay, but after some time, when change ceases to be a change, they go back to the original. okay, but do not bother about it. I mean, since you raised the point, I explained this to you. But I mean, these are the details when you work out, when you go into as to what happens over a sustained period of time.